Okay, thank you for tuning in. I'm Tom Jordan, a research scientist at Plymouth Marine Laboratory, working with Stefan Simmis. Today I'm going to give an overview on technical developments we've been making to improving above-water reflectance processing using shipborne data. This work is part of a wider EU-funded project called MONOCLE, and MONOCLE has a general focus on using in-situ optical sensors to improve monitoring of coastal and inland waters. So measurements of water reflectance enable us to capture biogeochemical dynamics. In situ data, as we're dealing with here, is also interesting as it enables calibration and validation of satellite imagery, in particular the atmospheric transmission and subpixel variability. Ships are interesting as they capture horizontal variability in reflectance. So-Rad, the automatic solar tracking sensor platform, is distinguished by its measurement geometry. So this is shown in the top right, and as you can see, the sky radiance and the upwelling total radiance are measured at 40 degrees to the vertical. And alongside measurements of downwelling irradiance, the remote sensing reflectance can then be derived. The system is particularly well suited for ships and large buoys. In general, the taller the better, as sensor contamination is then reduced. When So-Rad was designed, there were some requirements that were set. In particular, the system was to be standalone in operation, except for cleaning, low power consumption, 15 watts, low cost, order €3,000 plus sensors, and also open source compatible, in this case with Linux on a Raspberry Pi 3B. So today I'm going to be describing what we call So-Rad at PML, which is a new versatile solar trapping platform to automate spectroradiometers on moving vehicles. So-Rad is distinguished by being affordable, low maintenance, and is underpinned by open source software. In addition to the So-Rad, a novel sensor, which we call the HSP, a Hyperspectral Pyranometer, is installed alongside. And this sensor measures partitioned, that is direct and diffuse, downwelling irradiance. And today we're going to give an update on the So-Rad installation during the MONOCLE field seasons, focusing on Lake Ballaton and the English Channel. And then I'm going to focus on how the combined HSP and So-Rad setup enables us to improve above water reflectance processing. Skylight can be divided into a direct component, that's an optical path straight from the sun, and a diffuse component, light that's first been scattered by particles in the atmosphere. The HSP, Hyperspectral Pyranometer, measures these components which both have distinct spectral signatures. Within the reflectance processing, we actually consider the ratios EDS over ED and EDD over ED, and the spectral properties of these measured ratios are compared with an atmospheric model in the top right plot. As you can see, the HSP measurements differ from the model both in absolute values and the curvature in the blue part of the spectrum. It's to be noted the HSP was originally designed with aerosol optical depth characterization in mind, and this theme was developed in more detail in John Wood's 2017 paper. And I've included an example plot from his paper here which shows how ED and EDS vary throughout the course of a measurement day. So there are two separate field seasons that have been used to trial So-Rad and the HSP within MONOCLE. The first of these was in summer 2019 in Lake Ballaton, and during this field season the sensors were mounted on board the T&E car ferry and they travelled backwards and forth on a 1 kilometre transect. The second field season, from summer 2020, was in the Western English Channel, centred on the ports of Plymouth, Cherbourg and Roscoff. During this field season, the sensors were mounted on board the Brittany ferry Amérique, and as you can see on the top right plot, the sensor is very high above the surface of the water. Unfortunately, due to COVID, there's a gap where there was no out-of-port data. So a key challenge in water reflectance processing is accounting for spectral and temporal dependence of sky glint. A recent innovation in this regard, termed 3C reflectance processing, employs a spectral offset term delta to achieve this. The core equations for the 3C method are shown here. As you can see, the delta term corresponds to a sum of the EDD over ED and EDS over ED ratios that I introduced earlier. Now, the previous implementation of 3C uses the Greg-Carder model for a cloudless maritime atmosphere to define these ratios. The idea is that by using the HSP instrument, we're able to measure these ratios across a broad range of measurement conditions, varying from sunny days to cloudy days to fluctuating atmospheric states. And by using these estimates, the hope is that the 3C inversion scheme will be better constrained. So I'm now going to show a typical sunny day example from the English Channel. Sunny days are characterised by relatively low EDS over ED ratios, and this is shown in the time series here at 420 nanometers. I should say that gaps in the time series are where the quality control has been failed, and we think this is likely due to sensor shading. So the most notable feature is that in the blue part of the spectrum, the HSP variant of the 3C algorithm gives systematically higher reflection estimates than if the Greg-Carder model is used in the processing. This ultimately relates to the curvature of the optimized glint corrections, and this is shown in the top right plot. And as you can see, there's greater curvature for the Greg-Carder variant, which results in systematically lower values. Okay, so we're now going to move on to a typical cloudy measurement day, again from Roscoff. Cloudy measurement days are characterised by relatively high EDS over ED ratios. So as you can see here, EDS over ED is close to 1 throughout the day. So the reflection spectra again differ between the two versions of the 3C algorithm. So the HSP version of the algorithm has lower reflection estimates in the blue part of the spectrum compared to the Greg-Carder version of the 3C processing. Perhaps more interestingly, though, is the difference in the variability in the blue part of the spectrum. So the bottom right plot shows the reflection values at 420 nanometers. And as you can see, there's a much greater fluctuation in the blue points, which is the Greg-Carder model, relative to the red points, which is the HSP version of the algorithm. And both of these features relate to the Greg-Carder inversion being unable to replicate a white glint response. So to understand why the HSP version of 3C gives lower variability, we can now consider the correlation coefficient between LT over ED and the total glint, which for convenience I'm now calling LR over ED. So the top plot shows the spectral dependence of the daily standard deviations of RRS for the two versions of the algorithm as before. On the bottom plot, I'm then showing the spectral dependence of this correlation coefficient. And the key thing is that the higher variability for the Greg-Carder model for the reflectance is associated with a lower value of the correlation coefficient. You can really see this drop off in the blue part of the spectrum. By contrast, the HSP version of the algorithm has a high correlation coefficient over all wavelengths, which is associated with the lower RRS variability. So I'm now going to finish with some summary statistics on the RS variability for the Western Channel dataset. This is based on around 50 days of coverage. The top plot compares reflectance variability at 420 nanometers for the different variants of the 3C algorithm. An additional category here is 3C HSP where the sky radiance sensor has been removed, and this is in orange. These are subdivided into two categories: clear, partially clear days and cloudy days. And as you can see, on the cloudy sky days, the HSP variants of the algorithm have lower variability than the Greg-Carder variant of the algorithm. And following on from the previous slide, this relates to the correlation coefficient between LT over ED and LR over ED, that's the optimized glint. And as you can see, for the HSP version of the algorithm in red and orange, this correlation coefficient is significantly higher on the cloudy days. Okay, so time for a quick recap. So-Rad is a new automated solar tracking platform. It's standalone operation, low power, low cost and open source. The HSP is a novel sensor employed alongside So-Rad that measures partitioned downwelling irradiance. I hope I've convinced you that by combining HSP and So-Rad in reflectance processing, we can produce different estimates to before and potentially improve the uncertainty or the variability of our reflectance estimates. More details about the project as a whole can be found on the MONOCLE website. And please feel free to email both me and Stefan if you have any more questions. Thanks for listening.